Okay, we're talking about output analysis, which is basically what you, the whole purpose of, in a way, this whole modeling thing is, as I've mentioned, to answer questions. And what we've identified, and we have a very modest goal here. We could spend the whole quarter just talking about various ways of torturing simulation models to get them to confess. And why is that important? Because, well, why are we doing a model for analysis in the first place? It's because there's something that we don't know. Because if we knew it, then there'd be no point to doing any of this. And so in a typical simulation, and one of the reasons for doing a simulation model in this context is that there's no analytic model that can answer the question. And just as an aside, if there is, in almost all cases, an analytic model is going to be superior to a simulation model, which is kind of a weird thing to say at this point. You say, well, if that's the case, why have you been talking about simulation? Why didn't you tell us about this other thing if it was better? Do you get why we've been talking about simulation instead of these analytic models?
Analytic models aren't practical.
Well, yeah, I'm not sure about the expensive part, but in terms, yeah, you're spot on. In other words, the assumptions that go into typical analytic model that are necessary to be able to write down those equations are often very unrealistic. In other words, for the kind of queuing models that we've been looking at, if everything inside is an exponential distribution, then you can actually often come up with formulas for these things. That's part of queuing analysis. On the other hand, well, what the formulas are typically for are steady state of these analytic models, which we're going to talk about. And up to now, we've been talking about terminating analysis, which is where kind of the early part of the simulation. And there, even for many of the so-called analytic models, there is not a closed form solution for the transient portion. So in a way, it's like, well, you probably heard the story of guy, walking in the dark, and he comes across a guy who's under a lamp at night, and he's kind of looking around on the ground, and sort of how he says, "What are you doing?" He said, "I'm looking for my keys." He says, "Well, where did you lose them?" He said, "Well, in that dark alley back there." "Well, what are you doing here?" "Well, it's so much brighter here." And well, so that's kind of the why of these simulation models were created in situations where the analytic models didn't cut it. Okay, so before going on to steady state analysis, we've been talking about terminating analysis, and I've given you one example, and I want to give another example, and in the process also kind of show some little, just kind of a few little kind of tweaks on what that is. And then I'll start talking about steady state, which is, so let's see, do I have another slide on this? Yeah, so so last time I did a terminating analysis of the entity server, basically our multiple server queue, and now I want to do the same with our server with reneges, because there are so many more measures that were involved there. And so what this will kind of show is, just that relationship between the inner statistics, which we've been dealing with, and the outer statistics, which capture the statistics of the statistics, the mean of the means. And just as, and then just in the process, I want to kind of show a stopping rule and just sort of have a little class for this. So the way I want to analyze this, is I want a fixed number of potential customers. Remember, in the reneging model, we have customers who kind of come up, but they have this impatience value, where if they're not served by a certain amount of time, then they leave the queue. And where does that come from? It comes from the fact that we observe that happening, and maybe you've done it yourself. Whether it's a physical queue or, if you call tech support or something like that, and they put you on hold and you're listening to elevator music for a while, and then after a while it's like, okay, screw this, I'm gonna hang up and try something else. That's a renege, right? So the rule, the terminating condition is that after a fixed number of arrivals, potential arrivals have occurred, and whatever remaining customers in the system have either been processed or reneged, then that's going to be the terminating condition. Now, we don't have so far, well, we do now, but up until I wrote the little subclass of the customer arrival process, there wasn't a way to have that rule. In other words, what we had was, we either had this arrival process that just kind of kept coming. We had a variant of it that kind of stopped at a particular time, but that was only a subclass of the arrival process, not the customer arrival process. And what you could do is you could stop the simulation from schedule with a stop on event call, and say, I want to stop after this many arrival events, for example. The problem with that is that just kind of blows the whole simulation up. So as soon as that happens, it blows it up. And so it does not capture the fact that the remaining customers are being processed. So we don't have that. And so we need to have an additional little, component that's going to do that. And the principle of laziness says that, I have this for the server with reneges, I have this customer arrival process that was creating customers, scheduling the arrival events that would be heard by the server. So I had all that in place. And so rather than redo that, I want to subclass that and just add the little piece that I want. And that's kind of, and then, well, the other one, the other thing is, well, we'll get to when we start analyzing. So let's come back to that. So where is, okay, this is in the class code, so you can okay, I call it, my biggest challenge is sort of coming up with names. So I call this a customer arrival process limited, meaning that they're going to be a limited number. So as you see, it's extending the customer arrival process. And it's just adding a single parameter. I call it arrival limit. That's how many arrivals I'm going to have. And so all I want to do is I want to make sure the arrival events get canceled, but any of the pending, the server is still kind of going on. I'm not canceling anything in the server. I'm just shutting off the arrivals. And since it's extending the customer arrival process, which had 3 random variables, it had the inter-arrival time generator for the time between arrivals. It had a service time generator that would generate the service times and give them to the customers. And then it had the renege time generator. So I need to put all those in. And then add to it this arrival limit, which is just going to be, this is how many I'm going to have. And so, okay, so in addition to the constructor, and I see, I forgot the 0 argument constructor. I better put that in. Hopefully I might get to it later this week, or just to the questions about why this zero argument constructor. Excuse me. Okay, so really, okay, so hey, I have setters and getters on the parameter. I want to make sure that that arrival limit is a positive, or at least this should be less than or equal to. But, now, the only thing I'm doing is I'm overriding my do arrival event, which is that's the one that is all the way in the superclass of the superclass in the arrival process. And so I do want to invoke that because most of the time I want the next arrival. But then if that because those are now on the event list, I want to say now, if I've reached my arrival limit, then I want to interrupt. I need to interrupt two events. Remember that there was the plain arrival event and then the arrival event that had the customer class. So remember the arrival event in the customer arrival process, actually, let's see what that is. We see that it calls this its super, so that scheduled the next plain arrival, but then it would schedule an arrival event with the customer. Okay, so that's how I'm going to handle that. Okay, so now before I get to the analysis, let me just review here's our entity server, which we did last time. And the key thing is we're adding to the analysis, we want the number of replications. And I chose 30 because 30 is something I can pass the buck on in terms of why 30. The central limit theorem, just, and as I mentioned last time, I mean, is that really something real, or is that something somebody just made up? Anecdotally, 30 seems to work pretty well in my experience. And sometimes it's not enough. And sometimes it's more than enough. So, and likewise, alpha 0.05. Why alpha 0.05? Right? Because that's what the two choices are 0.05 and 0.01. Why? So the lesson there is like, not that first of all, to be real, to not have any illusions about these being laws of nature. These are things that somebody just kind of made up. They're sort of good. The main reason to choose them is they're defensible. And you don't have to argue with, in other words, instead of arguing with me about the number 30, talk to my stats professor, because that's where I got the number 30. Read the stats book, it says 30 somewhere. So, just the lesson is not that something is necessarily right or anything, but you don't have to argue about it. You don't want your brief kind of derailed by, some silly rabbit hole if you choose like some odd number. Okay, so so in this case, we're doing transient analysis. In this, the ending condition was a stop time, a particular stop time. We're going to do that differently in a second. And the main difference here is, if you recall, and you may have wondered about this, notice that we would have two calls. We'd have a reset call to schedule or event list for the Python one. I'll do the Python one in a moment. And then a call to start simulation. And this is one of the reasons why, because after the reset, we want to but before we start the simulation, we want to reset, that is clear all of our inner stats so that none of the data that goes into them gets carried forth to the next replication. We want to guarantee that the next replication will not only be independent, but we're not carrying over any data from the previous replications, because that would, of course, destroy independence. So what does this accomplish? It means basically before any event occurs, what this schedule reset does is it actually calls reset on all of the sim entities that have been instantiated, all of the simulation components that have been instantiated. Remember that if it has a state variable, it has a reset method. What is that reset method? That's what, this is a giant reset button that calls all of those. And so what that guarantees that all of your components are going to begin the replication in their initial state. Because see, notice we've wrapped it in a for loop. After you return from start simulation, you're at the end of, at the end of that replication. In this case, the time would be time 10,000, and your state variables would be whatever they are, whatever they're left at the end. And if I want to run another one immediately with the same object, if I run it, if I don't do anything, then I'm going to start with whatever state I was in last time. And that will destroy identically distributed, because I'm now doing a replication, but with different initial conditions. Okay, so between reset and start simulation, I have to do all this stuff. And so now the principle of laziness says, well, maybe that's a lot of work. It hurts my fingers to do all that typing. So is there kind of a better way? And there isn't. And what it takes is exploiting that feature where these reset things get called. And so in order to accomplish that, and this, I say, I really like these tiny little, this is a tiny little class. So here, it's a sim entity base. It has no state variables, but it has a parameter, which is an array of stat objects. And notice that the type is an abstract simple stats, which is the abstract superclass of all of the different statistics objects. What that means is that I can put any of the inner statistic, actually any of the stat objects in to this, because it's declared to be the superclass. If I didn't have that, then I'd have to have a separate one for the tally, the time varying, the collection ones, et cetera, et cetera, et cetera. And I'm lazy and I don't want that. And so all I need to do is I'm writing a reset method that just buzzes down all of these stats and just resets each one. And because it's a sim entity base and it's got a reset method, what that means is that reset method is going to get called before anything else, before start simulation. And so this will, so basically all I need to do is take all of my inner stats, put them in here, and then they will all get automatically reset. Okay, so that's that. So let's take a look at, let's see, where did I put it? Okay, yeah, so this, so we're gonna analyze the server with Reneges. And so, and I'm using the same parameters that we had when we were doing it as a problem. So I'm going to run it for 1,000 customers, 1,000 potential customers, 1,000 arrivals, not all of which will make it in. So here's my limited arrival process. So I'm just giving the same generators, and then I add the additional one. And just sort of by the way, and this is just a convention, but it kind of keeps things from getting too wonky. The convention is that when subclassing a simulation component that has parameters, you typically will need to pass all of those parameters to the superclass. And so in the master constructor, the one that has all of the different parameters, you put them in order of in other words, you put the ones in the superclass first. So in the in the customer arrival process, without this, it put the inter-arrival time generator first because that was in the superclass of the customer arrival process. And then here, the service time generator and the Renege time generator were in the customer arrival process. And then finally, the last ones are the ones that we had. So there it is. And there's our server with Reneges, and then we need to make sure that's listening. We've done all this before. here are our inner stats. They are the same, the number in Q, which is going to collection because the state is a queue of the number of available servers, and then the delays and the time in the system, which are tallies. So notice we have three different classes in the inner stats. And then we simply add them as a property change listener, because otherwise they're not going to hear anything. And then, all I need to do now is I need to create an array of these guys and then put it into this guy. And if you want to sort of see them there, but the printout from that is kind of ugly, so I commented it out. And then, of course, the simple property dumper is something which is important when you are debugging to make sure everything is working right. And then, okay, so we're doing this the same way as before. We have number of applications. We choose an alpha. And then because sometimes these can take a while, just for my own sanity, and I suggest for yours too, when you're doing something like this, is before I even start running, I'm going to say, okay, I'm going to run for this many replications, and this is the ending condition. So before I'm running, I print that to make sure that happened. If I don't print anything, and I may be just staring at a blinking cursor, and I don't know if it's actually running, or maybe it bombed out somewhere or got stuck in an infinite loop. Okay, so replications. And now notice that now I can just go back to reset and start simulation, because that class that I wrote, this inner stats resetter class, is now going to do all the resetting for me. And it's going to do it at the right place because it gets called from reset. But I still need to do the outer stat stuff. Now, and one of the reasons for doing this here is that sometimes I'm not just putting the results of the stats in. You mean? In this case, one of the measures that I wanted to look at was I wanted a confidence interval on the percent of reneges in this transient interval. And that's not something which the stats are collecting. That's something that I can compute from the objects themselves. And kind of now it's exactly how to compute that. It's a little bit tricky, but well, in this particular case, I don't need the other, but I did it anyway. So it's first I have the number of reneges, and then I have the number of arrivals. And now in this particular case, I could leave it at that. So that, but in situations where I don't run it to be empty, I will subtract the customers in the queue. Why? Because the customers in the queue, I mean, I want to estimate the percentage of reneges. So I know how many arrived. And I know how many reneged. But of the customers who are in the queue, do I know whether they reneged or not? Do I know if they got served? I don't know. You just don't know. So if I subtract those, because those are ones I just don't know. In this case, that's always going to be 0. So it's not necessary. The other thing that I typically am interested in is utilization. And again, I'm not collecting utilization. I'm collecting the number of available servers. So, and now this is fairly straightforward. The student T quantile is going to be the same. I need, here's my p-value. You subtract 1 from the degrees of freedom, all that from your stats, and then do the half-life. So when I run that, and it runs pretty quickly, then, okay, so in this case, I have a confidence interval for the number of reneges, the number in the queue, et cetera, et cetera, et cetera. And let's see where I'm looking. Yeah. Yeah, utilization, it's a little bit on the high side. The percentage of reneges is also a little bit on the high side, so, and notice it's sort of plus or minus like 0.6 of a customer, so, I'm sort of confident, fairly, hopefully, that it's kind of around there. Now, for those of you in Python, I'll do this quickly. It's the same sort of thing, but in the renege file, I put here's the limited customer arrival process. It's exactly the same logic. Where I have an arrival, I call the super arrival, but then if I'm equal to the limit, then I
Sorry,
cancel
I think
the
you're not
arrival.
sharing your screen.
I'm not, sorry. Keep forgetting that. Thank you. Okay. Okay, this is in the renege file. Yeah, again, have the constructor has all these things. I need to call the superclass constructor. Now, the one thing I didn't do here is check to make sure that I'll say if I need to if this is say less than or equal to 0, then I want to raise a value error, and I want to say that there are different ways of doing this, but this is okay. And so if I hit the arrival limit, and by insisting that it's positive, then that's always going to be okay. I need to cancel the arrival. And here, because Python doesn't have method overloading, there was a separate customer arrival event that got canceled there. When to analyze it, let's see, the analyze server with reneges, the same deal. There is an inner stats resetter, which is in the MV332 classes, and it's exactly the same as before, as in the Java one, where I have this array of inner stats, and then at the reset method, I call all of the oops, I forgot to do the although that's not, that's not going to affect anything in this particular case. So, and now here, it's a little bit different. There's I have some in SimKit quantiles. I implemented the student T stuff, and you just call student T with the p-value, the replications, and that gives you the half width of the various ones. Again, using the inner resetter, I don't need to reset them as I did previously, but I still need to do the same deal on doing the computations and putting them into the outer stats. So running that, let's see, run that, then again, notice I sort of print this before it runs, and then I have confidence intervals for the different measures. Okay, so that's the transient analysis. Okay, so now, what about steady state? So the thing about in the transient analysis, one of the things that characterize it are it depends on the initial conditions. If I change the initial conditions, I'm going to get different values. So if I started my model with, let's say, 20 customers in the system, then I'm going to get a different answer. Steady state is the opposite. Steady state is where the initial conditions, ideally, should not have any influence. And in fact, the initial conditions are typically not typical for steady state. In other words, for our queuing models here, we've started them empty and idle. But in steady state, they're not going to be empty and idle. They're sometimes going to be empty, and they're sometimes going to be 1, sometimes 2, sometimes 3, etc. In other words, there is a single probability distribution in steady state. In other words, in steady state, what characterizes a steady state is it actually fluctuates in a probabilistically consistent way. So steady state isn't just a constant, it still fluctuates, but it fluctuates about a probability distribution. Now, if I knew what that steady state probability distribution was, then I would know everything. What's the problem? The problem is I don't know what that is. Well, just to try to connect this. In your probability class, did they ever talk about Markov chains? No? Okay. Don't forget I said that. Okay, so our steady state measure, it may be very different from our initial observations. In other words, the system as it behaves in the initial parts is typically going to be very different than the way it behaves if you run it for a long time. And in fact, the initial observations are typically biased with respect to steady state measures, and I'll show you a graphic on that. But in steady state, we still have some of the same problems that we have, that we talked about for the simulation data. Now, of the two assumptions that went into what constituted a random sample in your statistics class, remember, they're independent and identically distributed. Now, in steady state, it turns out, in steady state, the observations are actually identically distributed. So that's great news, right? Except they're still autocorrelated. So only half there. So here's what it, and one of the big problems is, how do we know when we're in steady state? Now, well, if I could refer back to this thing that they call a Markov chain that you don't have to worry about, but Markov chain is an example of an analytic model. It's a stochastic model, and one of the it's actually a very cool model. So if you're ever bored on a rainy afternoon or something, you can kind of Google it and check it out if you're weird like me. But one of the things about it is you can actually solve equations that will tell you what the steady state distribution is, which is pretty remarkable. And actually, in fact, you can not only do that, but you can actually calculate the transient distribution as well as a function of time. It involves matrix, some advanced matrix stuff. But, Now, what's the problem? So here's the situation. If you remember, in the transient period, we had a problem with the fact that our successive observations were all different. And so if I'm looking, so what does it mean? What is the meaning of taking the average of delays in queue for the first 100 or even 1,000 customers when they're all different? In other words, what does a statistic mean when your observations all have a different distribution? And the answer is that in and of itself, it doesn't mean anything. You have to kind of add some verbiage. So what we came up with, if you remember, was the expected average delay in queue over, whatever the period was. In steady state, so here's in steady state, though, we only have one. In steady state, there is one steady state distribution, And it has, so like, we're after that unknown mean. We want that mean, this red horizontal line. This is the true but unknown steady state mean. That's what we're trying to estimate. And what this is this is a hypothetical plot of the actual, no kidding, values. In other words, this is the no kidding steady state mean. This is the no kidding transient mean over time, or over, over observation, however you want to characterize it. Oops. Now here's the problem. This red line is what we want to estimate. It gets very sensitive. Now, supposing we run our simulation up to this point, and these are our observations, and this is what we are measuring. And if I were to take the average of that, that would probably be around here somewhere. In other words, this is called bias. A bias is a bad word because bias is not a good thing. And in this case, it's not a good thing. Why? Now, what is the statistical meaning of bias? Do you remember? Yeah, exactly. In other words, if I have a biased estimator, then as I take more and more observations, I get closer and closer to the wrong thing. In other words, so let's say, unbeknownst to me, I've run my simulation, and I'm doing this. I'm operating it the same way I've been doing for the transient case, and I compute my confidence intervals and my mean, and it comes up with this value, which is roughly what it would be. Now, if you remember, like, one of the ways to kind of get a more accurate estimator is to take more observations. So if I take more observations, I get closer and closer to this value. And I'm more and more confident. I am so confident that I've nailed my steady state mean here. But this is the one that I want. So in other words, that's why is bias bad? Because the normal way of getting more accurate estimators gets a more accurate estimator of the wrong thing. So what is the what is the cure? Well, it's the well, let's see, you can ask your grandparents about who Henny Young was. He was a comedian. And he had one of his running jokes was go to the doctor and say, what's the problem? It hurts when I go like that. Well, don't go like that. Okay, so bias is bad. Bias hurts. And so don't go like that. Yes. Well, no, what this, what the blue line is, this is the, well, yeah, in a sense, it kind of is, except that what this is graphing is like if this were customer numbers, this would say be the true delay in queue of the 100th customer. So these are the successive averages, or if this were time, let's say if this were the number, the expected number in the queue at a particular time as time goes on. And yes, it does. I mean, ideally, it does tend to approach it. In other words, the millionth customer might be in steady state. But the problem is that if we've included all of these observations, they're still gonna be biased. They're gonna introduce bias. In other words, every observation in your sample that does not have the right mean is going to distort your final value. Yeah. So yeah, so basically, in other words, at some point, and we don't know what that point is. So that's kind of one of the things we're gonna hunt on a little bit, because finding that point where you reach steady state is actually, there are hand waving methods. Most of the methods that are kind of out there basically kind of wave their hands. Some of the fancier methods will have a whole bunch of math and then wave their hands, which to me is kind of ridiculous. There are a handful of, to me, statistically valid approaches, all of which require math that would take us another quarter just to learn. So we're going to punt on that a little bit. So the procedure is going to be, we're going to somehow figure out a truncation point and then throw away all of the data before then. In other words, this is also called warming up your system. In other words, we're going to run it up to this point and then throw away these observations. That's the idea. Why? Because I mean, as you was correctly pointing out, yes, that they eventually approach the true one, but they're still introducing bias. And so once I'm kind of here, once I'm fairly close, then I can maybe run it for a while and then maybe have a fighting chance of having values that are very close to the one that I want, instead of ones that are pulling it away. And this now, this is kind of one of many typical ways that steady state can be approached. There are other situations where it actually kind of goes like this. And there are even many, there are almost as many as you can kind of come up with. So this is kind of canonical in the sense that, well, for our canonical measure of delay in Q, since we know we always kind of start at 0, this is typical for delay in Q. So, okay. So basically what we're going to do is we want to truncate. And so the initial observations, they're biased. And so we're going to run the simulation for a while, and then we're going to clear the statistics and then carry on. So mathematically, if we have a tally, and then these are all on the inner stats. So for a tally data, if our truncation point is our T, maybe I should have called it capital N or something. What we're going to do is we're going to, the T, now T is the discrete one. So we're going to throw away all of the observations before observation T, and we're going to collect N more of them in this for a tally. So our mean is going to be just the sum, if these are the successive observations, the sum from the next one to the 1 plus N. And if it's time-varying data, then T is typically going to be a time. And so then our average after truncation is, let's say we run it for S time units after that. And since our time-varying mean is the area under the curve, we're going to just integrate, as if you will, between our truncation point and our truncation point plus the amount of time that we were kind of doing it. What does that look like? That would look like, remember that our state transitions are kind of going to look like that. And so if our truncation point is T here, and we're going to run it for, say, S t, up until time t plus s, then we would only compute, in this case, the area under here. And the hope is that if we run our simulation long enough so that we're at least in steady state, what we've essentially done is we have made one observation from steady state. If we do this, if we warm up and we actually reach steady state, we've made one observation from steady state. And so that would be one. So whether it's a tally, so for the tally, it would look something like this. So we have our, and these might be successive delays in queue. So our total number would be t plus n. And what we do is we take these guys and we throw them away. And then we only use the data from this. And so what we've done is we've taken one observation from steady state, if we've done this right. And then we have the autocorrelation problem, because they're still autocorrelated. I mean, in principle, we could sort of stop with just one observation, but that's kind of wasteful. What we want to do is these are typically positively correlated, although you can create situations where there's a negative correlation, which is kind of another. But as hopefully the little thought experiment about delays in queue illustrated, there's positive correlation. In other words, if I observe one longer than average delay in queue, the chances are the next one is also going to be larger than average, and vice versa. If I have one lower than average delay in queue, the next one's likely also to be lower than average. So that's autocorrelation. So because of that, in order to get kind of a more precise estimator, I want to kind of take a whole bunch of these. But at the end, whether I have a tally mean or a time varying mean, I still just really have one observation. Now, it would be nice if these were independent, that they are identically distributed, but they're still correlated. If they were independent, I could sort of stop here and just and have this be my estimate of the mean, but I can't. Why? Because autocorrelation means that if I want a confidence interval, my estimate of the variance of these data is going to be biased, and so will not give me a legitimate confidence interval. So what can I do? I can basically do this many, many times. In other words, if I repeat this and I've actually reached steady state, then if I have independent replications, then I'm back to a random sample. And as long as the rules for doing all this are identical, then I have an identical observation. Now, it also turns out that for the tally, sometimes we want to truncate not after a certain number of observations, but after a certain number of time. That's just kind of a thing. And then you don't have to kind of worry about the specifics of this, but basically, like in a tally, remember that we're kind of getting discrete observations. And so instead of counting them, instead of truncating like that, if we just sort of truncate at a given time, and then the thing is, we don't know how many we're truncating at. We don't know how many we're throwing away. But with the stats object, we don't need to worry about that because we just clear it out whenever the time comes. So tomorrow, or next time, we will we'll actually operationalize all this. Yeah, so yeah, what I described all this. This is it's called replication deletion. The deletion is the truncation. We're just going to repeat it many times, and it's going to be that we will go back over this tomorrow.